Okay, let's say you own an Android device and an Android phone. And of course, since you care about security, your Android phone is locked. It's protected either with a password or a PIN code or pattern. Now, let's say you somehow misplaced your phone. So, for example, maybe it was stolen from you, maybe you just lost it, or maybe it was even confiscated by law enforcement. And now the question is, can these people who now have your phone somehow unlock it and access the data that is stored inside? And there are a few non-technical approaches they can take to achieve this, but we're going to focus on a technical one. And since each Android device has a USB port, maybe there is a way then they can somehow attack it over USB. Well, normally, if you just start plugging in like usual USB devices into an Android phone, you will unlikely to get any meaningful result to achieve this goal. But if you manage to find a vulnerability inside the USB stack that is running inside Android, then theoretically you could use this vulnerability to overtake the Android device and thus unlock it. And this was the focus of my talk. So, hi, my name is Andrey, and I'm a security researcher, and I mainly work with the Linux and Android kernels. And my talk is called Fuzzing USB with raw Gadget, and essentially this talk is about trying to find a particular type of vulnerabilities in the Android USB stack. So I'm going to start with briefly describing the USB attack surface, but the part that I'm going to focus on are the USB drivers. Then we're going to I'm going to explain what fuzzing is, and we're going to look into how to apply fuzzing to USB. After that, we're going to check out a few ways to emulate USB devices, but the way that I'm going to focus on is based on a Linux USB Gadget subsystem. And the main topic of the talk is I'm going to show you how I used a new kernel module that I developed called raw Gadget to do fuzzing to fuzz USB drivers within a virtual machine without any external dependencies. So it can be used in any type of a virtual machine, and it does not require any additional hardware. And finally, we're going to look at how to trigger USB bugs with Raspberry Pi Zero, and I actually have a Raspberry Pi Zero right here, and hopefully we're going to get to the demo where I'll show you how to trigger one of the bugs that I managed to find. All right, let's start. So first, let's check out the architecture of a typical Linux USB host. I've split this architecture into three parts. On the bottom part, we have the hardware layer, in the middle we have the kernel layer, and on the top we have the user space layer. And I'm going to describe this architecture from the bottom to the top. So every Linux host device has a USB port. And this port is physically connected to a piece of hardware that's called the USB host controller. This host controller knows how to communicate over the USB wire. And since each hardware device in Linux is supposed to have its own driver, the host controller also has a driver in the kernel. Then this host controller driver is connected to an abstraction layer called USB core. And behind this abstraction layer, we have the drivers for different types of USB devices. So for example, we have the HID driver, and HID stands for Human Interface Device. And this is the driver for keyboards, mice, and other types of input devices. Besides that, we have drivers for mass storage, which are flash drives, and we also have drivers for video devices and other, there is a lot of them. So this abstraction layer, the USB core abstraction layer, allows a developer to write a USB driver regardless of what host controller driver is in use. And finally, on the very top, on user space, we have some user space applications and user space daemons. So for example, when you plug in a keyboard and you start pressing the keys, these keys are going to be shown in the text editor you're using. And this text editor is also, I kind of consider it a part of the attack surface, and it's running in user space. So here, our goal is that we control the USB device, and we want to somehow attack the Linux USB host by controlling the device. And we can actually attack each of the layers that we have. We can attack the physical ports. So for example, there is a device that's called USB killer. And when we connect it to a USB port, it's going to charge itself from the USB power lines and then discharge 200 volts over the data lines, and essentially just electrocute the USB port and maybe also the part of the boards, maybe the host controller. And then there are attacks that can be used like on the very top, the user space level. For example, there was this old Windows attack where you plug in a flash drive into a device, and there is this autorun file that is on this flash drive, and Windows would just run it, and this way you could execute arbitrary code on Windows. So since I work with the Linux kernel, I targeted the kernel layer. And the parts I was interested in are the USB core and the USB drivers. The reason I didn't really care about the host controller driver is because different Linux devices might have different host controllers. And I wanted to find bugs in the Linux kernel that would affect every Linux device there is. So I wanted to find bugs in the part of the kernel that are present on every Linux device. All right, to find these bugs, I wanted to use an approach that's called fuzzing. And fuzzing is a way to find bugs in computer kernels, in computer programs, and it can also be applied to the kernel. So I have this definition for fuzzing. Fuzzing is feeding in random inputs into the program until the program crashes. And it works like this. You generate a random input, you execute the program and feed this input in, and then you check, did the program crash? For example, the program could have segfaulted. And if the program didn't crash, you just generate a new input and you keep going. And if some point the program crashed, that means great, we have found a bug because we generated an input that triggered a crash in a particular program. That is a definition of a bug, at least one of the definitions. So for example, if we have an XML parser, we would be generating random XML files, we would be feeding them into the parser and would be checking for parser crashes. And at some point, if the parser crashes, then perfect, we actually have found a bug, both a bug and a reproducer for this bug in the form of an XML file. All right, how would we apply this to USB? If we look at the definition again, so first we replace the word program with the word kernel because we're trying to attack the kernel. But then there are two parts of this definition that we need to address. So first, we need to figure out how do we feed data into USB. Do we use any special hardware? Maybe we use some virtual machines, maybe we use some other stuff. And the second thing is we need to figure out is what kind of inputs does USB accept in general? Like what data do we feed in? What's the protocol? And I want to start with the second part and talk a little bit about the USB protocol. And the most important part about the USB is that it is host-driven. That means the device, when a device is connected into a host, the device cannot just send data by itself. It needs to wait until a request from the host. So here on the right, I have a device, and on the left, I have a host. And let's say we plugged in a device into the host. So at this point, device cannot start communicating. The first communication is happening from the host side. And the host asks the device, like, what kind of device are you? And the device, for example, responds, I'm a keyboard. And this response is actually done, the device sends a few structures to the host. And these structures are called USB descriptors. These descriptors encode information about the device. So, for example, they decode the class ID, which is a keyboard, and they encode the device manufacturer and so on. And there's quite a lot of stuff. So now again, the device cannot just start communicating again. Now the host asks. The host knows how to handle keyboards, and now the host asks the device, like, what kind of keys do you have and what purpose do they serve? And now the device responds, I have this many keys intended for this purpose. And now the host says, all right, you're now connected. To which the device will respond, okay, this didn't fit into the slide. All right, so the key part here is that the device only responded to requests from the host. And this is actually happening. So, for example, if you plugged in a keyboard and you started typing in keys, you started pressing on keys, the keyboard cannot just tell the host by itself that this particular key is now pressed. The host needs to ask for it. And it works like this. So the host just keeps asking the keyboard, like, which keys do you have pressed? And it's asked, like, any keys pressed yet? The keyboard says no. Any keys pressed yet? The keyboard says no. And at some point, you press the key, and the keyboard is going to respond. Now I have this particular key pressed. All right. So the key part about the protocol is we cannot just send data, right? So the way a USB fuzzer would work is first, it would wait until a request from the host. Then it would generate a response to this request and send a response back. And keep doing this in a loop until at some point in time, the fuzzer also needs to monitor the host for crashes. And if at some point in time the host crashes, that means we managed to find a bug. Okay, this is like a high-level overview of how USB fuzzing would work. Now let's go back to challenge number 1. So we need to figure out a way how do we feed data into the USB. And I started looking for ways of doing that. And the first way that I found is to use the phase dancer board. And I actually have it right here. So this board allows emulating arbitrary USB devices. And essentially, this board has 2 USB ports, one on the left, one on the right. And one of them is plugged into a computer that you control. and another one is plugged into the computer you're trying to attack. And then on the computer that you control, you can run a Python library that allows you to receive USB requests and provide responses to them. And this way you can emulate devices. And of course, since we can emulate devices, we can use this board for fuzzing. The problem with this approach is that it requires hardware, and fuzzing with hardware is challenging. So for example, we need to monitor our host we're trying to attack for crashes, and if it crashed, we need to reboot it, and doing this with hardware is difficult. So instead, it would be great to have some kind of approach that works inside the virtual machine. So I kept looking, and the next thing I found is the USB reader module in QEMU. And QEMU is a type of a virtual machine. And this module allows the host to inject arbitrary USB traffic for the guest kernel that is running inside QEMU. And this can also be used for fuzzing. And there is actually a fuzzer, it's called Virtual USB Fuzzer. And yeah, it uses this QEMU USB reader module. So the great thing about this approach is that we don't need any hardware. We only need QEMU. But this is also a problem because this approach depends on QEMU. So we cannot use other types of virtual machines to do this kind of fuzzing. And this was also a problem for me, and the reason was that I wanted to use a fuzzer called syscaller, and I'm going to talk a bit more about it later. But the key thing about syscaller is it mainly runs on Google Cloud Engine, and Google Cloud Engine is another type of a virtual machine. And that Google Cloud Engine does not have the USB reader module. So this approach is great, but it was not quite what I was looking for. So I kept looking. And another thing that I found was the Linux USB Gadget subsystem. And this subsystem essentially allows you to take a Linux-based board, like a Raspberry Pi Zero that I have right here, and turn it into a USB device. So there is a way to configure this board, so whenever you plug it in over USB, it pretends to be a device. And the logic of the device is controlled by the software that is running on the board. Right, and most of the Linux-based boards, at least most of the popular boards that exist, they have the support for this. So the BeagleBone Black I also tested, and I had an Android board that also worked, and the Raspberry Pi boards they also work. And theoretically, if we have this kind of device, we can also use it for fuzzing, probably, because it allows you to define USB devices. And the problem here is that if you're using an actual Linux-based board, we still require hardware. But maybe we can figure out a way to get rid of this hardware requirement. So let's try to take a look into the architecture of the gadget side. So this particular feature of this board is called, this board pretends to be a USB gadget. So let's take a look at the gadget architecture and try to figure out a way maybe we can do something about it. So on the left, I previously shown you the architecture of a USB host. Now we're going to look into the architecture of a USB gadget. And here we're going to start from the upper part, so from user space. And the logic of the USB device that is being emulated by a Linux-based board is driven by a user space application. Then there is a gadget driver in the kernel, and this gadget driver defines the type of the USB device. So for example, there is a gadget driver for emulating keyboards, there is a gadget driver for emulating video devices, and so on. Then, similar to the host, we have an abstraction layer called USB Gadget Core, and behind this abstraction layer, we have the device controller driver. Unlike the host controller driver, this driver is for the device controller that knows how to communicate over the USB wire while being a device, not being a host, right? And then we have the USB port, which is supposed to be plugged into USB host. And this part on the left allows us to use a Linux-based board to emulate USB devices. So now the question is, if we want to use this approach for fuzzing, we need to figure out which gadget driver do we use. And if you use just the driver for keyboards, this of course means that we can only connect keyboards, which is not very useful when we're fuzzing. We want to connect all kinds of devices. So I started looking, and I found a driver that's called GadgetFS, and it allows emulating almost arbitrary USB devices. And the keyword here is almost. So the way GadgetFS works is when it starts, it asks the user space application for the USB descriptors of the device it's going to emulate. And then whenever this gadget stack receives a USB descriptor request from the host, the GadgetFS is going to respond to this request by itself without asking user space. If it receives other types of requests, it's going to pass them to user space and ask them for a response and then give it back to the host. So there are two problems with GadgetFS. The first problem is that GadgetFS does not pass all USB requests to user space. It responds to them on their own, to some of them on their own. And that means that if the same USB descriptor is requested twice, we cannot provide different responses. And providing different responses would be very useful for fuzzing because this would be likely to trigger bugs in the host. And another problem, which is actually a bigger problem, is that GadgetFS has validity checks for the USB descriptors that we provide to it. And that means we cannot send malformed descriptors to the host. We have to send the correct ones. And we want to send malformed descriptors because we want to trigger bugs. So initially, I wanted to remove these constraints from GadgetFS. I started trying to change the GadgetFS code, but it has a lot of legacy code in there, and also the interface is a bit unusual, so it was hard to adapt GadgetFS. So instead, I just implemented my own Gadget driver. This took some effort, but I managed to do it. And this driver, it works similarly to GadgetFS, but it allows you to emulate arbitrary USB devices. And the key differences are that all USB requests that this Gadget driver received, they're passed to user space to get the response. And then there are no sanity checks on USB descriptors. And I actually mailed this request to upstream. So I mailed the Linux kernel patches, and they were accepted in version 0.7. I think it was released, it was over a year ago. Right. And I have a GitHub repository in case you want to check it out with some examples and instructions on how to run raw Gadget. All right. At this point, we figured out we have our own new Gadget driver that allows us to emulate arbitrary USB devices. We still have that problem that we need hardware to do that. So what we could do here is that this part of the stack, the Gadget part of the stack, is going to be running on our Linux-based board. We can take a separately physical USB host. We could plug this board into the host and then run the fuzzer as a user space application. And this is a way to use the Linux USB Gadget subsystem for fuzzing, for physical fuzzing of USB hosts. Now, the problem is that we need hardware, right? And is there any way we can get rid of the hardware? As it turns out, there is. Linux actually provides a solution to this. And this solution is called the dummy drivers. So essentially, Linux has virtual host and device controllers that are connected to each other within the same kernel. So previously, we had the Gadget part of the stack running on a Linux-based board and the host part of the stack running on a separate host device. But here, we can actually run both parts of the stack on the same device, or like within the same kernel. So this all would be running within the same environment. And this is actually the key slide of my talk. So we have our fuzzer running as a user space application. We use raw Gadget to emulate arbitrary USB devices. We use the dummy drivers so that the USB devices this fuzzer emulates, they're going to be connecting to the very same kernel the fuzzer is running on. And this way, you can do fuzzing inside the virtual machine, or you can take an Android phone and you can just run raw Gadget and the virtual dummy drivers inside. And you don't need any external hardware. You're going to be fuzzing on an Android phone internally. And you're going to be reaching USB drivers from within the kernel. Right. All right. And yeah, this was the approach that I ended up using. And I actually integrated this approach into Syscaller. Syscaller is a kernel fuzzer that is developed by Google. And it was initially developed to target the Linux kernel, but right now it targets a bunch of different kernels. And it has a dashboard. You can check out the dashboard. The dashboard shows thousands of bugs that this fuzzer has found, and all of them are public. You can check out the bug. You can check the bug report. You can check out the C reproducers. So essentially, the C programs that you can run to trigger a particular bug. And I integrated USB fuzzing into Syscaller, and so far it has found over 300 bugs in different parts of the Linux USB subsystem. Some of them are in drivers, and a few of them are in the USB core layer. And the only thing that I failed to do so far is to actually exploit a Linux or Android device over USB. So there are 300 bugs, and these bugs affect some of the drivers, but not all of these drivers are present on an actual Linux, for example, in Ubuntu. And when it comes to Android, Android also restricts the set of enabled drivers severely. So maybe only a few of the bugs, they actually affect Android, but the ones that do affect Android, I failed to find a way to exploit them, at least so far. Now, I want to get to the final part of the talk, which is, I think this is the most awesome part. So first, when you're using Syscaller to fuzz the kernel, whenever Syscaller finds a bug, it generates a reproducer for this bug. And a reproducer is essentially a sequence of actions the fuzzer can do, or like the fuzzer can do to trigger a particular bug. So syscaller has a utility, a tool to run these reproducers. It's called sysexecproc. So essentially, when syscaller generates a reproducer, you can run sysexecproc and trigger the bug. And it works with USB as well. Because we're doing the fuzzing in VM, we take in the reproducer, we run it in the same VM, and we can trigger the bug that the fuzzer has found. But the key thing here is that the interface between user space and the kernel is stable. And it is stable in the way that we can use any type of a device controller or device controller driver. So which means we can take Raspberry Pi Zero. So we can take the reproducer that was generated inside the virtual machine. We can copy it onto a Raspberry Pi Zero, and we can plug this Raspberry Pi Zero into a physical host. And this way, we can replay the USB communications we generated in a virtual machine with physical hardware. Right. Okay, actually, let me try to show it. We still have 5 minutes. This should be enough for the demo. So here I have a separate Linux laptop. All right. And I also have Raspberry Pi Zero. So what I'm going to do is I'm going to plug this Raspberry Pi Zero into the laptop and let it boot. So what I'm going to do now is, this demo is kind of weird because I need to show you the screens of both my laptop and the laptop I'm trying to attack. So I'm going to be using a web camera to record the screen of the laptop I'm trying to attack. Okay, let's see if this works. Okay, we can see something. All right, so this laptop is running, essentially it's Ubuntu kernel. And the kernel version is quite new. We see it, it's from April 22nd. So essentially it's 1 month old. All right, so what I'm going to do is on this laptop where I plugged in the Raspberry Pi Zero, I'm going to run the dmessage -w command. It's having trouble to focus. Dmessage -w command, which is going to show us the kernel log in real time. Right, and I'm not actually, so for this demo, I'm not running the most basic version of Raspberry Pi Zero. I'm running the version with Wi-Fi, and it's called Raspberry Pi Zero W. And I configured this board in a way that when I plug it in, it boots and it sets up a Wi-Fi point. So instead of using a bunch of wires to connect to the Raspberry Pi Zero, I'm going to be using a Wi-Fi connection. I'm just going to SSH onto the board. Okay, now let's see if we have the Wi-Fi connection. So on some technical conferences, actually, this demo has a problem. Oh yeah, we do have it. Because Wi-Fi is being attacked all the time. It's very hard to connect, but here it worked. All right. Now we have SSH onto Raspberry Pi Zero. So on the left, we're going to see the part of the screen that is recording the kernel log of the device we're trying to attack. And on the right, we have the connection onto the Raspberry Pi Zero that is plugged into this device. So first, we need to insert the raw gadget module. And now what we're going to do, I have collected the reproducers for the USB bugs that syscaller found. And I have them right here. So this is a special syntax that syscaller uses to describe reproducers. So essentially, sysUSB connect means that this particular line is going to emulate a type of a USB device, and the type of the device is described by all of these arguments. So what I'm going to do is I have this run script, and this run script essentially runs sysexecproc that I showed here. So I'm going to do run repros sysbot. And it takes a little bit of time to initialize. So essentially, what this is going to do, I have about 391s to be exact, 391 different USB devices that will be replayed one after each other. And this Raspberry Pi Zero is going to be connecting these devices to our physical host. And let's hope that this works. Okay, now it started. So as you can see, on the right, we have the log from the part of the code that is emulating USB devices. And on the left, we can actually see in the dmessage that the new devices are being connected. And if we wait for some time, I'm not sure. Yeah, at some point, I think this particular sequence of crashes. So at this point, you can see that the message is stopped. That usually means that we managed to crash the USB stack that is running on the Linux laptop. And if you could look, I don't have the mouse here. Okay, now we got something. So actually, the mouse is broken right now. I mean, the touchpad broke because touchpad is connected over USB, and we likely killed the USB stack on the machine. So you can see a part of the stack trace that was triggered, and yeah, this is just some generic stuff. So probably something bad happened. The problem with running reproducers like this is that some of them corrupt memory, and without running a memory corruption detector on the device, it's hard to tell what exactly happened. All right, we're running very low on time, so let me quickly finish the presentation. So yeah, this was the demo, so it worked. All right, so the summary is that I tried to attack Android and Linux devices over USB, and I tried to find bugs in Linux kernel drivers. So the result of the work is that I used raw Gadget, and I used the dummy virtual controllers that allow fuzzing either in the virtual machine and on the device. And this was integrated in Zscaler, and I managed to find a way to run these reproducers via hardware without any additional hassle. And yeah, by using Raspberry Pi Zero and raw Gadget, we get a very cheap tool for USB attacks. So essentially, Face Dancer costs about $80. This tool costs about Raspberry Pi Zero is only for $10 you can buy. And finally, one final note, very important, that Zscaler is hiring. So just in case you want to work on Linux kernel fuzzing or Linux kernel security in general, there is a team at Google, and they are here in the Munich office. And they are looking for a new team member. So if you want to work on Zscaler, this is the place you can apply. So with this, thank you. And we have no time for questions, so just in case you can catch me at the break and ask all of your questions.